Hi, I've been told that my last name is difficult to pronounce, so I came up with a little pictogram. So one of the pathways to whole brain emulation is reconstructing large-scale whole brain connectomes and simulating them. But if you think about it, this has never been successfully done. Even for the small brains, like the C. elegans connectome, which has about 300 neurons, and the completion of this connectome was my first foray into connectomics. We don't know how to simulate a behaving worm. And the question is, what is the problem? You know, we have this amazing level of detail, and what is missing? And what I think is missing is understanding of what happens in the nodes of this network. What exactly should be the transformation that describes neuronal function? It's not because of the lack of available models. You know, biological neuron is an object of incredible complexity, and it has been often reduced to models of different levels of abstraction. You know, starting from perhaps overly simplistic McCulloch-Pitts Rosenblatt neuron that is now called ReLU and is a foundation of all artificial neural networks even today, which definitely doesn't capture a lot of what the biological neuron does, to overly biologically detailed models like Huxley-based simulation. The problem with which is, of course, you know, they try to capture the firing of neurons, but there are so many free parameters that cannot all be measured that you have to fine-tune them, thus losing generalizability. And of course, there are intermediate level models, but the point I'm trying to get across is that no model provides a valid computational primitive of what a neuron does on the level that, say, logical gates provide a computational primitive for semiconductor electronics, for transistors. So there is nothing like that for biological neurons, which may seem shocking, but that's the state of affairs in neuroscience. And that's why I think people cannot, even having the connectomes, simulate behavior of even small brains. And so my group's scientific program is to generate such a computational primitive that could be put into the nodes of the connectomes to enable whole brain simulation. And the approach we've taken is called normative in neuroscience, which is what it means is that it explains function as a solution of some kind of optimization objective. We like to start with principled objectives like optimal prediction of future inputs, which is important for survival, and control, which is also necessary for interacting with the world. And we do this on a single neuron level. And the idea is to derive a solution to this optimization problem in terms of an algorithm that meets the constraints of biological hardware. Specifically, we want online or real-time processing because the data is streamed to you by the world. We don't want to rely on large memory storage because neurons don't have access to it. And of course, there cannot be an action in a distance, which is prohibited by physics. And so then, once we have such an algorithm, we map it onto an actual biological neuron, and we hope to capture essential physiological properties such as membrane potential, voltage dynamics that generate spikes, and the plasticity of synaptic connections that gets you synaptic weights. And we want to do it all in a self-supervised setting so that we don't need to measure too many parameters in real biological neurons, but we learn them from the data. And this way we avoid the problem of too many free parameters and ill-conditioned models. So we did it in a couple of settings, and you know that distinguishes our work from what was done before, because, for example, for prediction, there is information bottleneck work. Also, we did work on similarity matching that kind of followed this path. But the new aspect is that now we apply this in the dynamical system setting. What that means, we acknowledge that the world around us is constantly changing. It's a dynamical system, and so is the environment of each individual neuron. We try to capture it mathematically in this kind of framework. And then if a neuron were, for example, attempt to control its environment, then traditionally what you do is so-called model-based control. You learn the parameters of the model A and B from the previously seen observations X, D, and actions of a neuron's output UD. So D is for data. That's the training data that the neuron uses to find the parameters A and B of the model, and then to find the control law W. So that's very difficult to do computationally in such a small biological device as a neuron, and so perhaps that's why people have never done this before. So the innovation here is the new framework for control that is called direct data-driven control, which was invented about 20 years ago by Williams and company. And what they do is, in a sort of very machine learning spirit, they avoid this intermediate creation step, which is a creation of an explicit model of the environment, instead mapping the observations to the controls directly. And that mapping is learned on the same training data that was used to systems identify AB, but without explicitly representing AB. And the miracle of this approach is that once you take that path, you can actually come up with an algorithm that is biologically plausible. And an example of this is this expression we derived that mimics a neuronal learning rule, or so-called spike time independent plasticity. Not going to explain in detail what that means. Neuroscientists will know. If you don't know, it's a mainstream learning rule that is used in neuroscience. And another thing that we did, so that's on the time scale of synaptic learning rules, and on the time scale of membrane potential, we looked at prediction, again in the context of linear dynamical systems, and you want to try to predict a time series like this. In the linear dynamics case, you can fit it by a bunch of exponentials plus noise, and the goal is, of course, to predict, is to extract the fastest growing exponential with a linear filter, and this is the filter we learn from the data without any additional parameters, and they actually correspond to those experimentally measured in neurons. So that's the idea, that now we don't need those to measure those parameters. We can learn this all from the data and come up with a self-consistent description of a neuron that we call the smart neuron, which optimizes prediction or control and may serve as a foundational building block of the networks or connectomes that can be used now for the whole brain emulation. And I want to thank my collaborators in this work.
Who didn't ask a question?
Oh my God, it's Jason. Huh? We did our doctorate together, Jason.
He's great.
He's the best, yeah.
Is anyone who hasn't asked a question yet? Then I'll go for a few. Oh, take it away. Oh, you get a question?
Yes.
Go for it.
That really fascinating talk. Thank you.
Thank you.
Thank you so much. I was curious about those temporal filters that you learn. Is that related to does that capture the non-stationarities in any way, or how?
Yeah, so this is an excellent question, because much of the work in this domain has been done assuming the stationarity of the inputs that the neuron receives, which I don't think is always the right model for the real world. And so in this case, we actually used exponential functions, which cannot be stationary. So this can only be transients, but they are important to respond to, because if you don't, you can die. Like, think of swatting a fly, and the fly, watching the hand approaching, right? It has to respond to this non-stationary input. So that captures it.
Thank you.
Yeah. I was going to ask a question that it may be a dumber version of the same question. I'm not sure. I'm less mathematically versed. So it's a question I've had for a couple of the speakers. Is that I generally see an emphasis in these emulations or modelings towards neurons simply as spiking units when there's a lot of evidence in neuroanatomy and of slow wave, passive like current propagation, non-myelinated or non-synaptic signaling. And I wonder if those, especially when it comes to interoceptive, affective signaling is tremendously important. And I'm wondering, is there any issues with those types of signaling perhaps being overlooked, or is that accounted for also in these types of models?
So I have to be honest that we are still struggling with the spike in neurons, and we made the most progress with the graded potential neurons. And this model can, of course, be used as a firing rate neuron. But yeah, but that is, in our hands, it's much easier to handle than, a spike.
Oh, okay. Excellent. Thank you.
Thank you so much. Wonderful.